welcome to another module in this massive open online course. Alright, so we are looking at the demodulation of a double side band modulated DSBSC, that was double side band suppressed carrier signal, when there is a phase offset between the carrier that is generated at the receiver and the carrier wave component in the incoming signal. And we have seen that leads to poor performance. So, when the incoming message signal, so we have the incoming message signal, that is your AC MT cosine phi or cosine 2 pi f c t, this is your incoming signal, and this is demodulated or multiplied by the carrier which is locally generated at the receiver. And when there is a phase offset phi, alright, this is the carrier locally generated or locally generated carrier. And when this is passed through a low pass filter, our output signal is half AC MT cosine phi. So, this is an extra factor which is arising in comparison to coherent demodulation, correct. Coherent demodulation means when phi is equal to 0, that is there is phase synchronization, phase synchronism between the locally generated carrier and the carrier wave in the incoming signal. So, this is an extra factor in comparison to coherent we have already seen this, coherent and coherent demod means phi is equal to 0, and this leads to a power, the power of this, correct. Coherent demodulation means phi is equal to 0 and power, the resulting power equals 1 over 4 AC square, the power in the message signal times cosine square phi, which becomes progressively worse as phi increases, which means as phi increases, that is as phi increases from 0 to pi by 2, or as the phase offset as phi or phase offset increases from 0 to pi by 2, output power decreases to 0. So, the performance becomes progressively worse. Alright, this is what we have seen. Alright, now let us understand why this phase offset arises and why is it important to tackle this phase offset. Now, to understand that, let us consider for a brief moment a typical wireless communication scenario. Alright, it is clearly explained or it is much more apparent when you consider a wireless communication scenario. Alright, so let me draw a typical wireless communication scenario. So, what we are trying to understand is why does the phase offset arise. So, our question is why does the carrier phase offset or how does carrier phase offset arise in the first place. And I have a mobile, let us say a base station which is transmitting to a mobile. Okay, I am schematical, I am drawing a schematic of this is your base station, and this is your mobile. Okay, and this is the transmitted signal. So, the base station. So, we are considering a typical wireless communication scenario where a base station is transmitting a signal to the mobile, and keep in mind that the mobile user can be moving in this cell, alright. That is the important thing, that is the mobile or the receiver is not fixed, but the distance that is the user is mobile, and therefore, the scenario and therefore he is mobile and therefore he is moving, correct. And something interesting happens as the mobile user moves, as we are going to see shortly. Now, let us assume that this distance of propagation, this is the propagation distance. This is the propagation distance, okay. And let us say the transmitter, that is the transmitter transmits signal or transmits the signal xt equals mt, alright, or let us go back and let us say this is AC mt cosine 2 pi fct. This is a signal that is transmitted by the transmitter. Now, the propagation distance, there is a distance between the transmitter and receiver. So, the signal takes time to propagate from the transmitter to the receiver, and the time of propagation, the propagation delay obviously depends on the distance between the wireless transmitter, that is the base station, and the mobile receiver, alright. And the propagation delay is specifically given by the distance d divided by c, where c is the speed of light. So, the propagation delay, now once the signal is transmitted, realize that there is going to be a propagation delay d by c, where c equal to the speed of an electromagnetic wave, or c is basically your speed of light. Now, as a result of this, the signal received, that is yt, is actually not exactly xt, but xt minus tau, or let us call this delay tau, and therefore, signal received at the receiver, the signal received at the mobile user the signal received at mobile user is yt, which is xt minus tau, that is, remember, delayed version of xt. Naturally, signal xt minus tau implies basically the signal xt delayed by tau, and therefore, the signal yt is now, if we substitute for xt, this is AC, of course, AC is a constant, mt minus tau cosine 2 pi fc cosine pi fct minus tau equals AC mtt minus tau cosine 2 pi fct minus 2 pi f c tau. Now, substituting tau equal to d over c, this is a c m c, or not m c, a c m t minus tau cosine 2 pi f c t minus 2 pi f c. Now, substitute for this tau as d by c. Now, you can see this is the phase offset phi equals, this is phi which is equal to, this is your phi which is basically equal to the phase offset. Okay. Now, of course, we are not going to see this in detail, but we can also say m t minus tau is approximately equal to m t, because the delay, because remember the message is varying very slowly. The maximum frequency component f m of the message signal is much lower in comparison to f c, which is the carrier frequency of the, carrier frequency. Therefore, for small delays tau, one can say that m t minus tau is approximately equal to m t. All right, since the message is varying since the maximum message frequency f m is much lower than f c, correct. Since the maximum message frequency f m is much lower than f c, I can say therefore that this is approximately equal to a c m t cosine 2 pi f c t minus d by minus 2 pi f c d by c minus, let us write this as the phase phi, which now depends on the distance d. The phase phi of d equals 2 pi f c d by c. This is the phase offset, the variable phase offset, or the varying phase offset. And the most important thing is, you have to realize that this depends on the distance, the varying phase offset phi, which depends on, or which is a function of the distance d, which is a function of the distance d of the user, and that is the important thing. So, as the distance d of the user is changing, you remember the user is mobile, and therefore, as he is moving, the distance d is changing. As the distance d is changing, the delay tau, which is d over c, is changing. As the delay tau is changing, the phase offset is changing, and therefore, even though the transmitter, the receiver, the locally generated oscillate, the locally generated carrier at the receiver might be synchronized with respect to the incoming carrier wave at some point in time, very soon, because the user is moving, the phase offset of the carrier component in the incoming signal is changing. All right, and the rate of change, in fact, you can realize, you can see easily, depends on the rate at which the user, that is, if the user is stationary, of course, the phase offset is not changing, but if the user is mobile, right, this phase offset is changing, and the rate of change of this phase offset depends on the velocity of the user. If the user has a very high velocity, then naturally the distance is changing at a very fast rate. The distance is changing at a very fast rate implies that the delay tau changes at a very fast rate. If the delay tau changes at a very fast rate, the phase offset phi d changes at a very fast rate. Therefore, you can clearly see this quantity d phi d by dd, if you can look at this quantity, it is let us call this d phi d, or let us just denote this by partial derivative d phi d by dou d, which is equal to dou by dou d 2 pi f c d by c, correct, or dou phi by dou t rather, which is equal to 2 pi f c by c dou d by dou t, and this is nothing but the velocity. The rate at which the distance d is changing is proportional to the velocity of the mobile user, which means if the user is mobile with a very high velocity, the phase is changing, the distance is changing with a very high velocity, therefore, the resulting phase offset is changing at a very high velocity, which means that there is frequently a loss of phase synchronization between the carrier wave in the incoming signal and the carrier wave that is locally generated at the oscillator. And this frequent loss of synchronization means that there is going to be deterioration of performance because of this phase offset, and hence one has to constantly keep resynchronizing at the receiver in order to avoid this deterioration of offset, in order to avoid deterioration of performance arising from this frequent loss of phase synchronization, and that is the importance of synchronization or phase synchronization, because this phase synchronization is constantly being lost because of several factors. One of the main factors is because the user in a typical wireless communication scenario is mobile, which leads to a varying delay, and varying delay leads to a varying phase offset. Okay. So, this leads to varying delay. So, let us summarize this. Varying delay implies, so varying delay or varying distance, let us put it that way, let us start with varying distance implies a varying delay implies a varying a phase offset. Further, the rate of change of phase offset is proportional to the velocity of the user. Hence, to avoid loss of performance, deterioration, one has to frequently synchronize phase of locally generated carrier with that of the incoming carrier signal, or local oscillator which generates the local carrier with that of incoming signal. One has to frequently synchronize. This process is termed as phase synchronization. This process is termed as phase synchronization. This process is termed as phase synchronization, and it has to be carried out frequently in order to avoid any performance deterioration at the receiver. And how is this phase synchronization carried out? This phase synchronization can be carried out with the help of a Costas receiver. And to perform phase synchronization, one can employ Costas receiver or a Costas loop. What the Costas receiver does is basically it synchronizes the phase of the locally generated carrier with that of the carrier component in the incoming signal, thereby making that aligning these two phases, right, making sure that the locally generated carrier is synchronous, right, is in sync with the carrier wave component in the incoming signal, thereby avoiding the performance deterioration that arises from arises otherwise from non-coherent. That is why that basically it aids in coherent demodulation. The Costas loop, by synchronizing the phase of the locally generated carrier with that of the incoming signal, it basically enables coherent demodulation. That is the whole idea. So, Costas loop, basically Costas receiver enables coherent demodulation by synchronizing phase of the locally generated carrier with that of the incoming phase of the locally generated carrier with that of the incoming signal. Local generated carrier with that of the incoming signal. Alright. So, that is basically the idea why we need phase synchronization. So, what we have seen in this module is basically we have seen a practical scenario of why this carrier phase offset arises. This arises because in a typical wireless scenario, the distance, right, the propagation distance between the transmitter, that is in the downlink, alright, the user can also be a transmitter, but typically in a downlink scenario where the mobile is transmitting, the base station is transmitting to mobile, and this is also valid for an uplink scenario, alright, because the distance, it is symmetric, right. So, in a downlink scenario when the base station is transmitting to the mobile or the mobile is transmitting to the base station, because the user is mobile, the propagation distance is changing, which results in a varying delay, alright, varying propagation delay, and that results in a varying phase offset of the incoming signal with respect to that of the locally generated carrier at the receiver, and therefore, phase synchronization is important, and this is carried out using a Costas law. Alright, so we will stop here and continue in the subsequent module. Thank you.